Hi everyone, my name's Franklyn, and today I'm really excited to talk to you about Ecne, the first ever verifier for zk arithmetizations. Let me give a quick review because I know you've seen a lot of zk proofs these last few days. Zero knowledge proofs allow someone to prove that they have a secret x so that f of x equals y, where f is a known function, also sometimes called a circuit, and y is a known value. zk-SNARKs are powerful because they let you do this for any function f, not just specific functions f. At a high level, zk-SNARK construction involves two phases. The first phase is converting the function f into a QAP, which is a set of degree 2 polynomial equations over fp. This is also sometimes called an arithmetization. This conversion process is often very manual. Second, this QAP is then converted into a zk-SNARK, and this process is mostly automatic. Now let me give you some examples of QAPs. So a very simple example. Y equals x cubed converts into x2 equals x times x, and y equals x2 times x. Hopefully it's relatively clear why these two equations are equivalent. Now a more non-trivial example. Let z be an array of size 2, and let y be z of I. Okay? So now let's let I equal 0. If I were equal to 0, then note that E1 equals 0 as well. Since E1 equals 0, and E0 plus E1 is 1, then E0 is 1, and by the last equation, y equals z of 0. This is kind of a tricky case, but hopefully it shows that QAPs can often be rather complicated, even if the functions are simple. This also reflects that QAPs are very powerful. Essentially, any function can be converted into a QAP, even functions that don't look like mathematical expressions. So why does this matter? So for a zk-SNARK to be secure, the translation from function into QAP must be exact. And it's especially important in zk because oftentimes, if a protocol has been exploited, we won't really know sort of by the design of a zk protocol. Today, QAPs are usually constructed manually, which leaves open the possibility for holes or ways that this function to QAP conversion is not exact. To show some examples in the real world where this has happened, there have been holes in well-known zk circuits. For example, Dark Forest, a very well-known zk circuit, had a missing bounds check, which led there to be a hole. Aztec's non-native field arithmetic also had a missing bounds check, which led to a hole. And note that these bugs will often appear completely without warning. So look at these two pieces of code at the bottom. They look very, very similar to each other. In both of them, you have an input x, and you have an output of size 3. In both of them, 2 times out of 0 plus out of 1 is equal to x. However, in the first one, out of 0 by this quadratic is equal to 0 or 1, and same for out of 1. Thus, x lies between 0 and 3. In the second example, we constrain out of 1 and out of 2. You might make this mistake if you have an off by 1 error, but all of a sudden, there's no constraints on x anymore. Circom will compile both of these with impunity. So we need to figure out a way to distinguish these. And Ecne can tell the difference. So if you run Ecne on the first one, it'll tell you that x is bounded between 0 and 3. And the second one, it'll tell you that x has no bounds. So this is exactly what we want. Before I further go into how Ecne exactly works, I'm going to define two terms that I use regularly: weak and strong verification. So the system of equations is weakly verified if there is at most one unique solution for the output variables given the input variables. And this is enough for most security purposes because we have an algorithm that gives us the output variables in terms of the input variables already. So as long as it's unique, then it's all good. The second type of verification is strong verification. Those of you who are familiar with formal verification will find these notions very similar. And this shows that a system of equations maps to a formal mathematical expression. So this system of equations defines a function. And this often requires complicated specifications for what that expression exactly is, which often are not available. To give a very specific example, say that we had a QAP for big integer multiplication. This is a relatively complicated QAP. So this big integer multiplication corresponds to x1, x2, x3 times y1, y2, y3 equals z1, z2, z3. We would consider this QAP to be weakly verified if we could show that Z1, Z2, and Z3 were unique given the values of X1, X2, X3, Y1, Y2, and Y3. For strong verification to be shown, we would need to show that the output Z1, Z2, Z3 of this QAP, which is a system of equations, satisfies X1, X2, X3 times Y1, Y2, Y3 equals Z1, Z2, Z3. So there's a difference here. And note that with strong verification, we can hope to use downstream properties of X, Y, and Z, whereas in the weak verification, we can just show that Z1, Z2, and Z3 are unique. So what does Ecne do? Ecne will take in a set of QAPs that are either weakly or strongly verified. We refer to these as trusted QAPs, and then try to weakly verify an input QAP. The first step in this process is using prior knowledge, where we find instances of trusted QAPs within this input QAP. So if in this system of equations, we see a subsystem of equations that we know corresponds to, say, big integer multiplication, we just replace it with big integer multiplication and don't waste our time on all these equations. Then we use an inference algorithm to weakly verify this QAP. So to provide a schematic, we start with this untrusted input QAP. We have a bunch of trusted QAPs. We run it through a prior knowledge engine, which gives us a simpler QAP plus some special constraints. So maybe there's like a big integer multiplication constraint now, not just our original QAP constraints. Then we run it through an inference algorithm. Now let me describe this inference algorithm. This inference algorithm works by maintaining a variable state which tracks currently known information about each variable. Some of this information includes things like, is this variable uniquely determined, which begins as true for both the inputs and 1. Is there a lower bound and an upper bound, as we saw earlier? And lastly, a very cute one, which I've never seen before, called an ABZ group. And an ABZ group is a group of variables such that at most one of these is not equal to 0, and we know exactly which one it is. Then we also provide a set of inference rules which tell us how to update the variable states. To give some examples of inference rules, the easiest inference rule is for a constant k, if k times z is uniquely determined and k is not equal to 0, then z is uniquely determined. This is relatively straightforward and follows from the fact that we're working on prime fields. Now some fancier inference rules. If A times X equals B for an invertible matrix A and B is unique, then X is also unique. Lastly, with the ABZ group, if X1 plus X2 plus X3 is unique and X1, X2, and X3 belong to the same ABZ group, then we know which one of these is non-zero, and that must be that unique value. Thus, all of X1, X2, and X3 are uniquely determined. Now let me talk about the inference algorithm. This algorithm works by maintaining a queue of equations that we consider to be promising. Okay, so this starts with variables, equations that don't have a lot of unknown variables. For every single promising equation, we try every single inference rule to learn about the variables. And every time we learn something about a variable x, say that we discover the variable x is uniquely determined, we push all equations that contain that variable, like y equals x squared, onto the queue. Even if these equations have already been processed, now that we know something new about x, maybe we can learn something about y. So for example, here we could conclude that y is uniquely determined. This step saves a lot of time because we only push equations onto the queue when we might make new progress on them. And this leads to the overall algorithm being linear time. Now let's talk about some of the very exciting results we got. Ecne can verify with no trusted functions 49 out of 76 of the circuits in circom-lib, which contains a lot of well-used functions. On the more practical side, let's first talk about the ECDSA circuit. This is a circuit used in Cabal, which we saw yesterday. And assuming the strong verification of big mult mod P and big mod, we are able to verify the ECDSA circuit completely. To give you a sense of scale, this is about 1 million equations in 10 minutes, which is many orders of magnitude better than you can do with a Grosvenor basis solver, the more natural approach to this question. It can verify tornado cache when we assert the weak verification of the Peterson function, which is an elliptic curve function from circom-lib. Now, tornado cache is a very well-used protocol. In fact, it's arguably the most popular ZK protocol. So this shows that Ecne can verify lots of production-level circuits. Recently, we also ran it on Hermes, and we discovered that it can verify Hermes rollup main with some asterisks that have to do with authentication, and Hermes withdraw no asterisks, with absolutely no assumptions on trusted functions. So this is also very cool because Hermes is also a very well-used set of circuits. Now let me talk about how we envision Ecne being used. So Ecne lets you show that something is verified, assuming that other things are verified. Okay? And this lets you home in on the exact conditions that are tricky to verify. So say that we can show that A is verified after we trust B, C, and D. If we can do this, it suffices to check B, C, and D and nothing else. So we only have to focus on B, C, and D, which dramatically reduces the surface area we need to focus on. For example, in the ECDSA circuit, I was able to show using Ecne that ECDSA was verified as long as big multimod P and big mod had no issues with them. We actually found an issue in big multimod P, and Ecne told us that we had to focus on big multimod P. Now let me look ahead to a frontier of something that Ecne cannot yet verify. Ecne can verify lots of things, but this is something we can't yet verify. And it turns out that happens for a very deep reason. Okay, so this is the addition function on the baby jub-jub elliptic curve. And initially it looks that everything should be fine. Beta is uniquely determined because it's the product of two inputs, same with gamma, same with tau, same with delta. Then we have that 1 plus d times tau times x out is equal to beta plus gamma. And we want to show that x out is uniquely determined here. And it seems like this should be fine. However, there's a problem. If 1 plus d times tau is 0, then all of a sudden, x out would not be uniquely determined. And initially, I thought this was going to be a real problem. It turns out it wasn't, though, because there's this paper that shows that 1 plus d times tau can never be 0. It's theorem 3.3 in that paper linked. But this is a very, very non-trivial argument, so Ecne wasn't able to come up with it, but that's kind of expected anyways. Furthermore, this also shows the limitation of our approach, which is that to show that 1 plus d times tau is non-zero, you need to use the fact that x1 and y1 lie on an elliptic curve, which is not something you can express in a variable state, because variable states only concern single variables, whereas this point lies on a curve concerns two variables. So some next steps are that Ecne's algebraic capabilities are relatively weak, like we saw in that previous example. It cannot reinvent all of modern mathematics, and it would be really nice if we had some more of these, right? I don't think this is a hugely pressing concern because most programs are not really inventing new algebra. And the ones we do need, like the baby ad curve I saw previously, already have some formal verifications of them, like this explicit formulas database from the hyperelliptic website. In conclusion, we're really excited about the potential of applying Ecne to all kinds of ZK circuits. And if you're interested in an audit, please do not hesitate to reach out to me at my email address here, which you can also get by this lovely QR code. Thank you.